Okay. As I already said, the second session is about the optimizer. Not only the optimizer, maybe mostly not about the optimizer, but also about the data access parts. I mean, algorithms used by the engine to retrieve the data from tables, to utilize the indices, to perform the sorting, and so on. So we'll discuss what are the problems in the optimizer area. We'll start with what were the problems in the past, how clever or maybe how dumb was the optimizer in the past, how did it improve in Firebird 2, and what problems are still remaining that are known to us developers and that we are working on the solutions, and what particular solutions you could expect soon. By soon, I mean, of course, Firebird 3, not earlier, but perhaps later some of the changes could be backported. I don't know. Let's see. The time will show. Originally, the optimizer was quite simple. Well, of course, simple is not really simple. The optimizer is never just a simple piece of code. It's a complicated logic, but unfortunately for the original optimizer authors, developers, you guys are making much more complex queries than in the prior years, and with some query generator tools, you could provide the engine with the queries it just couldn't optimize properly due to its high complexity and so on. And also, you know that we were adding some language features more and more, and of course many of them affect the optimization area as well. For example, when we introduced derived tables, the original optimizer was just not prepared to work with them. Of course, the optimizer is not really simple, but it was still quite suboptimal for many complex queries. What are the key points of the original optimizer we inherited from the Borland times? It was a kind of mixture of two optimization strategies. Some parts of the query execution was optimized using cost-based approach. The engine was calculating number of records, known as cardinality. It was calculating the selectivity of the predicate, how percent of rows will be affected by this predicate. And then the engine was trying to estimate the total cost of the execution. Unfortunately, this approach was used only to decide about how to join streams, how to join multiple tables. Almost everything else was not decided using costs. Just some hard-coded heuristics were used by the optimizer. For example, it was also always trying to use an index for sorting if it's available. For example, it will never use sort merge join if the index is available. That could make the nested loop join possible, and so on. But it's actually not the worst part of that optimizer, because that time very complex queries and very nested joins were not really common. Well, I know if you would disagree, but anyway, in the early 2000 and maybe a few years after that, we didn't have such complex queries as now. But the most problem was related to compound indices, because the engine had just a single value of selectivity for the index. So if it's a single segment index of single column, of course, the selectivity can be used for pretty much everything the engine needs it for. But as long as you have a compound index involving 2 or more segments, and your query only first 1 or first 2 of them, this is known as a partial match. This selectivity value just didn't make any sense for the partial key. It makes sense for the whole key, consisting of all segments. So any retrievals, any queries that were using such a partial matches, we optimized really badly. And a lot of hacks, a lot of workarounds have been used by people trying to avoid these situations and improve the plans and so on. And another problem was that the engine couldn't really good optimize complex joins of 6, 7, and more streams. So if you join just a few of tables, it was okay. If you join 8 or more tables, it was a big problem. For example, if you join 6 tables, the plan is good. If you add 7 one, the plan becomes worse. If you add another one, the plan goes just inverse, and the performance just degraded significantly, and you could never successfully wait for the statement execution until it completes. These were the major problems, and in Firebird 2.0, a lot of work has been done by the Firebird team, in particular thanks to brilliant Arno Brinkman, our Mr. Optimizer, that was very active that time. The optimizer code has been a lot of changes were made, has been not completely rewrite from scratch, but maybe a half of the optimizer has been changed. What were the key changes in Firebird 2? Well, I call it the second generation of the optimizer, just because of the number of changes made in that Firebird version. First of all, we have introduced new kind of index selectivity, specifically selectivity related to the every index segment. So it required us to introduce new ODS version, but thanks to Firebird 2 being the major release, we already had Firebird 11 introduced that time, so it was not a problem to add new statistics to the database, but it automatically resolved any optimization problems with partial matches of compound indices. So it's not longer an issue starting with Firebird 2. The calculations are as good as possible with just using the selectivity values. Then, another known problem was inexact calculation of the cardinality, number of rows. The engine, of course, cannot just count them because the table could be big enough, and so optimization will take a lot of time. So it just used some estimation based on number of data pages and the length of the record and its estimated compression ratio, how much the record is compression, so how many records could be fit in the single data page and how many data pages exist in the database. This worked quite well for big tables, and it worked really efficiently. but it provided us with very bad estimations for small tables that consist maybe of just 10 rows, 100 rows, and so on. So a better, instead of just estimating the number of rows, we just detect that the table is small. By small, I mean that it consists of just one database, and we just count all the records on that database. It requires just a single page fetch, so it's extremely cheap. But of course, if you consider a complex join of, for example, 5 or 6 tables that is started from the sum of the smallest tables, the difference between estimation of, for example, 10 rows and 1,000 rows gives a lot in terms of the cost, wrongly estimated cost. So this change really allowed us to really optimize access, especially complex join with small tables, some kind of directories, and so on. Then, the selectivity value is good enough. It allows us to see what part of the entire row set will be affected by this particular predicate resolved via the index. But it works only for equality comparisons. This is just the idea of the selectivity. It can be used only for equality comparisons. If you join or maybe just select from some table and using a greater than operator, the selectivity is useless. But Firebird 2 and the new optimizer had a solution for that. We had introduced some artificial selectivity values that can be used for non-exact, non-equality comparisons, including not only greater than, but starting with, like, and so on, containing. Then, a more exact cost calculation has been implemented in Firebird 2, this second generation of the optimizer, because it started to account not only how many records will be read from the table and how many data pages will be accessed, but also how many index leaf pages will be accessed before finding the necessary key or a number of keys. So if we speak about not unique retrieval, but some range retrieval. So it allowed us to, again, better estimate the total cost of the complete retrieval. The join cost calculation has been improved. The algorithm has been changed so that it doesn't have problems anymore with more than 7 or 8 tables joined. So the plan is still as good as possible for the optimizer. Of course, as you perhaps know, the optimizer never checks all the combinations of tables, because it's just terribly long time is going to take. So the optimizer always try different first tables, throw away surely bad choices, then start to add new tables and so on. So there is just a time-consuming optimization. But in Firebird 2, the optimizer was clever enough to optimize 10, 12, 20, or whatever number of tables, and still being fast enough to do it in the reasonable time. At least I have never heard of really big optimization mistakes related to joining many tables, starting with Firebird 2. And another big feature was to push the external outer predicates, we call them parent predicates, into subqueries, including unions and groupings, aggregations. Before that, if you join a table to a, for example, derived table, including a group by clause, the second part would never use an index. starting with Firebird 2, provided that you join by the field that the derived table is grouped by, so it doesn't affect the resulting set. It can be pushed inside the subquery and used inside the subquery to utilize indices if possible. Of course, there were much more changes than this list, and perhaps I don't even remember every of them, but the key ones, the primary ones, and the more important ones have been listed on this slide. Please notice that it's not only about Firebird 2. It's about Firebird 2 and database in ODS 11. Because of the new statistics, we have decided to split the optimizer in two parts. One part is working with legacy databases, ODS 10, and interbase databases, and a completely different optimizer works with Firebird 2 and ODS 11. So if you want to benefit from all these changes, maybe a few of them could be available even for older databases, but a number of them, the major number of them, is available only for ODS 11 and above. So if any of you is still running Firebird 1.5 in production, you should seriously consider whether your database and your applications experience problems with the optimizer error, and if so, think about moving to Firebird, at least Firebird 2.0, even if it's not supported anymore, or better Firebird 2.1 and Firebird 2.5, just because of the optimizer. I know that not everybody really needs all these improvements, because a lot of OLTP applications just use a very simple queries, and most of the retrievals are based on the primary key and so on. So it could be not a problem for them at all. But if you have a mixed load, both OLTP and OLAP, and if you have a lot of queries entered by users, ad hoc queries and so on, it could really affect you. So the better optimizer will always be better for you. But one thing that could be delivered from this slide is that the optimizer is working good only if you have an up-to-date statistics. So if you have never heard about the set statistics statement, and if you perform a backup restore cycle once a year, well, using the new optimizer, you could be in problem, because you have to update the statistics regularly. If it's wrong, the optimizer is also wrong. Well, you know, miracles are not possible. The optimizer just cannot guess from the heaven what is going on in your database and how the data is distributed and so on. Let's now switch to the topics that we know still giving us problems, even with the second generation optimizer. Not because the optimizer is bad, just because there are still a lot of areas that require further attention, better optimization, and as I said, your query is becoming more and more complex. So the optimizer just have no other choice but to catch up and trying to satisfy complex queries of modern applications. I have already said that the cardinality, it's a number of records in the table, is currently estimated based on how many data pages exist in this table, how big is the record, and how good it is compressed. Well, this really gives quite a good estimation, but there are exceptions. For example, until very recently, we didn't know really and couldn't even guess about the record compression ratio. There was a hard-coded constant that every record is compressed twice in size. Well, in some cases it was good assumption, but in some cases, of course, it's not going to work and provide really good estimation. So in the recent Firebird versions, and I mean both Firebird 2.1 and Firebird 2.5, maybe it was starting with Firebird 2.1.4 and Firebird 2.5.1. We have added an estimation for record compression ratio. So we just sample a few records, find the average compression ratio, and then utilize it in the later calculations. So far, so good. But let's look at the data pages. How many records can fit single data page? Well, we know record compression ratio, know the length of the unpacked record. Good. But let's remember that we have MGA engine. And every table has a lot of versions. And not every of them can be visible for your application, for your transaction. And even more, not every of them is visible to anyone at all. It could be garbage. Moreover, small blobs can be stored at the data pages, thus making records quite fragmented. So less records fit a single data page. Moreover, some data pages could not have records at all. I mean primary record versions that can be accessed by the transaction. It could contain only record versions invisible, record fragments, if the record was big enough to be split among multiple pages. So these pages should not be counted when estimated the cardinality. These are the problems known now, existing now with calculations. Of course, in many cases, the current approach is good enough, but it doesn't mean that anything better is not possible. It's surely possible. We just need more statistics and more exact statistics. Not only estimations, but some data known to be true for some moment of time. Then, let's go to the index scans. To find some key in the index, we need to go from the index root page down through the index tree to find some leaf page, one or maybe more, if it's the range retrieval. But how many levels will be read? We don't know. Of course, if your database is big enough, not really small, it's likely to have 2 or 3 levels in the index tree. We know that, and we have 3 levels hard-coded. But it's not an exact estimation. Again, we know nothing about how index keys are compressed. Firebird use prefix compression for index keys. For some keys, it saves maybe about 30%, sometimes 50% of the key. Usually, the compressed key is twice smaller than the original key. But if we speak about an index with a lot of duplicates, the prefix compression works very good in this case. And many index keys, all the duplicates, will be stored just 1 or 2 bytes, giving us up to 10 times of compactification of the index key. So any hard-coded estimation is not going to work. We cannot just guess that every key is twice less. Sometimes it's bigger, sometimes it's less. So this information could also be useful to understand how many leaf pages will be read by the index scan. Then, we have the selectivity. It can be used for equality comparisons. So far, so good. But imagine you have 1 million records, 1,000 of them have some kind of unique values, and the rest are nulls. What will show you the selectivity for nulls? Completely nonsense value. So if you then query for is null, the estimation will be completely wrong. Moreover, if you even query for equality, some index key equal to some constant value, you should not count all the nulls that exist in that field, because the equality comparison can never match them, can never see them. But we don't know how many nulls are in the table, and the selectivity tells us nothing about that. So this is also a problem for nullable fields that are indexed. And the mostly known problem, maybe for everybody here, is that Firebird supposes uniform value distribution. It means that if selectivity is, let's say, 0.1, is that we have 10 different keys, and every of them occupies 1/10 of all the records. In many cases, this is not so. If you have a very skewed distribution of values, the selectivity is unlikely to help you much. So, the common solution to this problem is to use a value distribution histograms. If you work with other databases, you know what it is, and this is what Firebird could have as well. But although I know that many our users just vote for this feature without stopping and crying when it's going to happen and so on, it's not an ultimate solution at all. Mostly because it works only for comparison with constant values. If you use parameters, the optimizer does not see parameter values when preparing the execution plan, so value distribution histograms are useless. So it's not a silver bullet. It's just, it allows you to optimize some of your queries better, especially if you have some kind of flags that only a couple of maybe 3 value is used, and mostly they are hard-coded as constants, or something like that. In these cases, it's going to help a lot, and avoid choosing bad plans involving scanning index that should not be scanned in this case. But in other cases, it's not really going to help a lot. So just think about it as a good feature, but not an absolutely good feature. Well, there are always cases when whatever information you have at hand, the optimizer will not be able to guess the rest anyway and decide what you really mean to do. So it's a solution, but only for some cases. And one more thing we are lacking is selectivities for non-indexed columns. Currently, the optimizer just do not use any. Well, we have only statistics in the indices. They not exist besides the indices. So if you have, for example, an index-based retrieval, when one field is going to be matched against the index and another is not indexed, you don't know. Well, you know that the index retrieval or index scan will give you, for example, 1,000 of records. The selectivity helps. Okay, then this 1,000 of records will be filtered using the second predicate. It was not indexed, but you don't know how many records will be filtered out. You don't know what will be the remaining cardinality of this stream. And this is a problem. Okay, of course, the optimizers make some guesses. It had some, again, some hard-coded constants in this regard. But a more general solution could be possible, just to have selectivities not only for indices, but for every column, to know its selectivity, its value distribution if it's not even, and so on. This is just about statistics. But, of course, the optimizer itself and the data access algorithms it implements may also be sometimes suboptimal. One of the known problems is using procedures, derived tables, aggregations, unions in joins, especially in complex joins. The problem is that all these kinds of complex subqueries, complex derived tables, do not have any cost associated. So the optimizer, when joining them to each other or maybe to some simple tables, cannot guess about the total cost of the join. So it just decides to go the easiest way. Consider him to be costly enough, it puts them first in the join order. Well, if the second stream is a table and the index is available, that could be good, because it will be a classical nested loop join using the index scan on the driving table. Fine, excellent. But if the index cannot be used for the second stream, we're in problem. If you join two subqueries to derived tables with group by and so on, you're in troubles again. So this is a known problem. Another kind of this problem, if you join procedures to tables. You know, if the procedure depends on the table via the input parameter, the regular inner join is not going to work. It will throw an error. So you have to work around it using the left join and so on for the join order by hand. Well, we know about these problems. And just a few examples. The second one is a famous issue with procedure dependent on the table. If you would write it this way, it's not going to work at all. If it's rewritten using the left join, it's going to work. The first example is a bit more complicated. It just shows a simple case of joining a table with some complex subquery. Well, it's not really so complex in this example just because of the limited space of the slide. Believe me, I could find some more complex examples, but they would be harder to follow. So, what can we see here? The subquery has a grouping by, ordering, and the first 10 clause. So, it's complex enough, but we don't know actually how complex it is, how hard it will be to execute this query, and what is going to be its cost. The engine is likely to put it first in the join order and then join it to the employee database. Okay, in this particular case, it's going to work. But if the example would be more complicated, or if it would be left join here instead of the inner join, it would be a problem. And actually, well, in the second example, we know a workaround using the left join. In the first example, I'm afraid there is no easy solution. You have to sometimes rewrite your queries to avoid such situations. Sometimes, if it's possible, force a join order via the left join again, but provided that the subquery could be indexed inside. Another, not really a problem, just a known issue with long join chains. If you join multiple tables, and especially if you not only use some condition on the driving table, the first table, and everything else just linked through the, for example, foreign key relationship. Yeah. So second, third, and other retrievals are made through the primary key. That's very good situation, and it's very efficient, and it's maybe a kind of ideal plan for the complex join. But the practice shows that it's not often the case. Sometimes you need to limit the record set not only for the driving table, but also for some other table in the join. And then the optimizer starts to think, should it use the limitation criteria to limit the rows, or should it continue using the primary key and join through the primary key? Joining via the primary key is as cheap as possible. But, and if the join order is made this way, it doesn't make sense to use any other index, because the primary key is known to deliver only one row. No other predicate will make less rows, maybe 0. but that's the maximum possible. But if we could try to change the join order, to start with some other string, the choice becomes a bit more complicated. The common solution to this problem to use hints. Well, not really hints, but hints, you know. +0, concatenate to the empty string, and so on. It just turns off the ability to use an index on the particular field. And one of the possible effects is that another index will be used for the same table. So you just disable some bad index and force the optimizer to use only good one. Especially this is important if you have a skewed value distribution, not uniform. So you just help the optimizer to understand this index should not be used on, it's bad. It looks like it's good because the selectivity is good enough, but actually it's going to deliver a lot of duplicates. So you just turn it off using the hint, and the optimizer starts to consider other options, and probably in most cases is going to choose the good one. But a more important effect of using the hints is changing the join order. Sometimes, however, the optimizer seems to be clever in other queries, you will find some query it will optimize badly. I mean complex joins. So use the hint +0 usually if you join by artificial keys to disable a particular join retrieval for that table. So the optimizer will never put it in the end, but will try to start from it. And it's not only, usually it's enough to make, to change the join order to add the hint to the table you want to see first in the plan. As it cannot be joined to anything via the index because of the +0, the optimizer will start from this table and try to join everything else. So the join order could be reversed, just changed in some way. It's usually going to be good enough for you. Of course, this trick could be done multiple times for multiple tables to force the join order you need. It's quite easy to do. Well, I'm sure many of you using it in production and so on. I never personally like hints and don't like suggesting them, but of course we know that even the greatest optimizers in the world, some commercial databases and so on, I know some people consider, for example, the Microsoft SQL Server optimizer being the best one around the world, but even in these cases it can fail. It's that simple as that. There is no ideal optimizer in the world. In Firebird, as you could see, we lack some statistics that could be used and so on. So of course our optimizer is suboptimal sometimes too. So hints are just unavoidable evil for not only for us, a lot of Oracle programmers use hints as well. So just a real life. You have to live with that. I've just outlined when and how it should be used. This is an example of one more related issue. Here's a not really complex query, but it's a join of 6 tables. We have 2 limiting conditions. One of the very small table region and a kind of between condition to the last 2 lines are for the quite big table orders. Let's switch to the real examples a bit. I'll try to show you with the plans. Here's this example. Let's just prepare the query. What can we see? The biggest table has been chosen is the leading table, and everything else is joined with a primary key. As I told, this is actually maybe one of the best possible plans to join multiple tables. But The first table is the biggest one. You can imagine how many times every next level will be called. How many times nested index retrievals will happen. So, for example, we have orders table. It's maybe 10 times less than the line item table. So every row from the order table is going to be read via the index 10 times. The same for all the other levels. It's just multiplying, expanding. It's a kind of enclosure to retrieve the entire join. What are the other options? That plan was good enough, and actually a lot of you could not even try to find anything better. But there is another option. We could join everything to the orders table, limit the orders table with the predicate. Well, it's going to be 1 year of orders. Maybe it will be 1,000, maybe 100,000, we don't know. The optimizer actually makes some guesses about that, it knows it better. But if everything is joined to the order table, which is already filtered by this condition, because this condition, as you could see, was not used in the plan I was showing you, and then join to the line item table, line item table is big. The remaining part of the join is big enough but filtered by the condition to be much slower than originally. So we have two streams. Joining them via the index is not going to improve the situation because we already used one index and nothing else is possible. But we know that the nested loop join is not the only option. Firebird supports also sort match join. And it doesn't need any indices. It works just with unindexed streams. And this is exactly the case when one part of the join could be done via the nested loop with index lookups, and then join to some other part of the join, or maybe to some other table via another join kind. Currently, in Firebird, it's sort match join. Another option is not yet available in Firebird 2. It's a hash join. And actually, the result is going to be faster than the currently chosen by the optimizer. So you see that sometimes the indices are good, primary keys are the best indices possible, but it doesn't sometimes deliver the best results. Some other solutions are possible. The problem is that the current optimizer never will try to avoid a nested loop join. It considers it being the best one. Sometimes it's not true. Another problem known is related to outer joins. Well, it's as simple as that. Only one join algorithm is used by outer joins, nested loop join. What's good is that really quite effective way to perform a join. What's bad? If you cannot use an index on the slave stream, you're in troubles. It's going to iterate through the second stream as many times as there are records in the master stream. So, absolutely artificial example, when you perform a left join and some function does not allow to use an index for a join, you will have a full scan for the employee table and a lot of full scans for the department table. If the department table is small enough, you are lucky. Otherwise, you are not. And in this particular case, for this particular issue, there is no workaround at all. Because the optimizer just doesn't have other join kinds available for outer joins. You cannot force the optimizer to use other options. So you have to change your schema to change your queries and so on to avoid such situations, or at least try to make the index lookup possible for the slave table. And one more part of the known issues is related to subqueries. Maybe it's kind of the mostly known set of problems. The obvious one is when you have a subquery which is not correlated to the outer query. It's not really a common case, but sometimes some such query exists, and you may perhaps notice them. Firebird has some optimizations for not correlated queries to avoid executing them again and again, but it works only for singleton queries. If it, for example, some aggregation and so on, if it results in only one row or even one more value, one more field. It just executed once, cached, and then all the predicates or whatever you are using that subquery do not cause it to re-evaluate again, but just using the cached value. Good, but if you are working with subquery that delivers multiple rows, this trick is not going to work, and your subquery will be re-executing again and again and again, depending on how much rows are in the outer record set. As I said, it's not really common, but it's a problem. Another two issues are much more famous and known to you. First of all, it's about non-indexed correlations. For example, you have a table joined to a subquery, to a derived table. Okay, that's good. And the subquery, the derived table, is written that way that it cannot use an index for a join. So there is a join condition that makes all these strings, the table and the derived table, dependent. But this join condition cannot be pushed inside the derived table because it just doesn't use any indices, so it's pointless to push it there. So actually, these two parts are dependent, they are correlated, but the correlational conditional is external. It's outside the derived table. So what this means, if the join order will be starting with the table and using the derived table as a slave, it will be re-executing again and again and again. If this derived table contains grouping by and stuff like that, maybe it could contain joining a few tables and so on. Imagine how complex is this, how hard it is to execute, and how much time it's going to take. It's just going to be terrible in the performance point of view. Of course, in such simple cases, the optimizer will try to start the join from the derived table. And in some cases, you could force it manually by using the hints. But it's not always possible. And sometimes such correlations really making the subquery executing a lot. Again, as the previous variant, it should be cached, but the engine cannot cache it to execute it only once. And the mostly famous example, it's implicitly correlated streams. It's about the in predicate. If you write a query containing the in predicate, you expect it to be non-correlated, but in fact, it's correlated. The engine optimizes this query. It tries to use possibly an index inside this query. So it transforms the in into some kind of exist. It takes the condition from the field which is compared with the in predicate, and the field from that is selected from the subquery. This condition is pushed into the subquery in the hope that it will be used an index. Usually, this hope is good and the index can be used. But a lot of you would expect that it works differently, that the subquery is just read once, cached, and then the outer table is probed against this cache. Nope, it's worked differently. So, if you are really not aware of how it's going to work, a more explicit solution could be to use exists instead of in. Actually, in some older Firebird versions, it was even a recommendation, because in was known to be slow and exist known to be fast. It's not true anymore. In all Firebird versions that I know, they are executed mostly the same way. They are absolutely exchangeable. But please be aware that not in is not the same that not exists. Accordingly to SQL specification, nulls are handled differently in exists and in. So for in, regular in, and positive exists, they are handled the same way. By negative in and negative exists, they are handled differently. So if you're just trying to rewrite all your queries from not in, for example, to not exists, using some suggestions found on the internet, be prepared for troubles if your subquery is going to return at least one null. The result, maybe you will expect this is the result you will have, but it's not the result the SQL specification declares that should be returned. Be aware about that. Examples. The first one illustrates exactly the case of joining a table to a subquery. As you can see, I have specifically forced the join order via left join, so the optimizer could have no other choice than to start with the employee and then join to the subquery. But the join condition is using the field which is internally in an aggregate function. It's an average. So there are just no choices for the optimizer to use the index for this retrieval. And the left join makes it impossible to turn the streams back to exchange them. So this query is going to be really slow. The same problem will be if you would be inner joining two derived tables of the same kind. Again, the index cannot be used. You have a problem. The good thing with the inner join is that the optimizer, after failing to find a good nested loop join way, it will try to use a merge join. It's going to work. It could be a little bit slower, but it will work. But look at the condition. More or one value is more than another. Neither sort merge join nor the hash join is able to work with non-equality conditions. So if it would be equality and then inner join, the optimizer would find a way to satisfy your query. In this case, it's impossible. So this kind of query is going to be slow anyway. And another second example is a simple one illustrating the problem with in. So if you think that the engine will read and cache the department table filtered by the predicate and then try the employee table against the cached record set, it's not true. Instead, the employee department field will be injected as an equality predicate to compare with department ID, and it will work a kind of join with the employee always being the master table and departments always being the slave table. But actually caching their inner table subquery is not the only option to improve this query. It's the most obvious one, but not the only option. You can easily add a distinct clause to the subquery and change in with join. The distinct clause will eliminate any possible duplicates from the slave table, but the inner join will make possible the optimizer to consider the costs and choose the join order that would work better. It could start from the department table and then join to the employee table. Moreover, if you know that the debt ID is a primary key, so it's not going to deliver duplicates, the distinct clause can be avoided. It will save you an absolutely unnecessary sorting, and you can still join the tables and allow the optimizer to do its best to find the proper solution. So sometimes it's possible to rewrite the query, delivering the same result, but allowing the optimizer to do its job and choose the best possible options without guessing how it's going to work, how it should work, and that I know it will work better to cache the subquery. The optimizer will do it itself, but if you rewrite it as a join. Just beware about the duplicates and the distinct clause. Sometimes it could be required. One other, not really maybe known problems, but it was registered in our tracker. So it's the performance of the external sorting. As you know, any order by clause, group by clause can be resolved by either index navigation, it's the order plan, or the external sorting, sort plan. Two absolutely different methods to evaluate, to perform the sorting. This is about external sorting, sort plan. How it works now? We construct the key, the sorting key. It's mostly about what you can find in the order by clause or the group by clause. Then the engine adds DB keys and transaction IDs of all the active records involved in the sorting. If you join 3 or 5 tables, it will be 3 or 5 DB keys and record IDs. And then to the sort record, the engine adds all the fields that were referenced in your query. Then such a compound sort record consisting of the key, DB keys, transaction IDs, and all the remaining fields you explicitly or maybe implicitly via the asterisk has enumerated in your query. They are added into the sort record, put it in the sorting module, which performs sorting in memory first. Then some big blocks of data are being moved to the temporary space manager when they are tried to be cached again. And then, if it's not possible, they are moved to the temp files, temporary files. So, why it works this way? Simply because we have only one path on the table. If this path is mostly in the storage order, regardless whether it's a natural plan or index scan, because of the bitmaps, Firebird, even in index retrievals, is trying to follow the storage order, to read records in the storage order. And after the sorting is completed, everything, all the fields are read from the sorting buffers, again, mostly sequentially, because the sorting buffers are known also as runs. They are already sorted by the key. So when the engine builds the kind of binary tree of these runs, so when it finds some run, it just reads sequentially all the rows out there. So there will be some kind of random reads when switching from one run to another, but mostly the database access and the temp file access will be sequential. It sounds good? Yep. But having to sort a lot of data costs you an extra input-output problems with temp files. So if the sort is big enough to not fit into the internal buffer, into the temporary space manager buffer, it's going to go to the temporary files, and you will have to write a lot of fields on disk and then read them again. And these fields are not directly related to the sorting. And as the sort model itself, the algorithm used to sort, they work with a fixed length fields and fixed length records. It means that every field is expanded to its maximum declared length. So if you have a varchar 100, for example, even if all your values are just strings of 10 bytes at maximum, every of them will occupy 100 bytes in the sort record, and so in the temporary file, finally, it will be swapped out. So, with big sorts, and especially in situations when you sort by a small key, but your select list has a lot of fields besides that key, and especially if those fields involve varchars and long chars and so on, longish things, and the record set is going to be big enough to be swapped out from the internal buffers to temporary files. This additional overhead with disk access to temporary files is likely to decrease the performance quite noticeably. So, how could you notice that? You should just compare the performance. First of all, you just find all the sortings that are done by small key, but some bigger fields retrieved along with that key. And then there is a workaround. Here you can see the example. Instead of just selecting the longish varchar in the same query with order by, you join the order by subquery with an added primary key, or it could be DB key. The primary key is just maybe usually smaller, 4 bytes instead of 8 bytes, and join with subquery against the same table again to get the varchar back. So the questions will be a bit later, okay? So you have 2 accesses to the same table, but it's still maybe 5 to 10 times faster. If you see 4 bytes key, 300 bytes varchar field, and of course if the table is big enough to be swapped out from the memory buffers. Of course, it's not an absolute solution because if you have a small page cache, after the sorting, all your records that you have read before will be moved cleaned from the page cache, and then when you will be reading the table again, you're likely to have a lot of disk reads. So actually, in some cases, it could be at least that bad as the original query, or sometimes maybe even worse. You should just check it yourself. With your setup, with your size of the page cache, with your size of the record sets, whether it's going to for you to work or not. For example, in our tracker, I don't remember exact numbers, but there were a few times of difference between these kind of queries. And in real applications, it's also about up to 5, I know for sure 5 times the difference. So just consider it. It's not an absolute cure, but sometimes it could be useful. Finally, what is going to change in this regard in Firebird 2? As you know, Firebird 3 introduces new ODS version, ODS 12. So it's a really good chance for us to add some missing statistics and some better support for the optimizer to work around or maybe completely resolve some of the issues discussed in this session. So we are going to introduce a lot of new statistics. You can see all the information here. There may be other statistical values as well, but these are the primary ones. This statistics is going to be stored in the database. These statistics could be complete, I mean calculated from the entire table, or could be sampled if you set statistics based on some, for example, 1/10 of the whole table. to just make some kind of estimation, but which is going to be faster, because it's not only about indices. You can see that value distribution for all the columns are going to be included, so it's actually calculating all the statistics for big tables. It's going to take a lot of time. So if you're going to recalculate, to update the statistics quite often for the whole database, it could be quite not good for you in terms of the performance. This is why we are thinking about sampling here. Here is the solution for the sorting problem I was talking about. We have it implemented, it's being tested. Of course, it's not going to be applied anytime. First, for example, imagine a query with a distant clause. All the fields in this select list are the keys. So it doesn't make any sense to make two passes against the table. Just use the regular approach that's existing since the Firebird beginning, and it's going to work best for you. But in some cases, if the optimizer could detect that the sort record is actually larger than it should be, that it could be, so that the difference between the whole sort record and the key is big enough, and that record set itself is big enough to likely to be swept out, so the optimizer could use this alternative approach to improve the sorting. The issue about subqueries. One of the obvious solutions is to materialize subqueries, cache them for the database, and access them internally by either joins or predicates and so on. Here, well, mostly this slide was presented the past year as well, because the code is ready and committed into Firebird 3 for a while. Just the optimizer is not using it now for all the possible cases. It will be extended, and we hope to have we hope to have all the cases covered by Firebird 3. But time will show how easy it's going to be. But at least some of the cases we hope to address using this approach. Firebird 3 have already implemented hash joins as an additional option to the merge join that could be used in complex joins, like I was presenting a bit earlier. Also, well, you could ask why we need hash joins if we have sort merge joins. But sort merge join works only with sorted input streams. If they have already explicitly sorted via the order by clause, for example, it's going to be the best option. But if your tables you are joining are initially unsorted, you will have two extra sorts for a join of two tables. If you join 3 or more tables, a lot of extra sorting just to perform the join. It's a lot of unnecessary work. The sorting operation is mostly, maybe one of the most costly operations inside the engine. So the hash join does not require additional sorting. It does require a single pass on the table to make a hash table, but it's way cheaper than performing sort to sort. And it's going to create a hash table only on the one table and only on the smallest of the tables, while the sort merge join is going to sort all the tables regardless how big or small they are. The hash join is committed and can be tested. It's just not tuned good enough for big tables. It now works better for small tables, but well, a bit of time is still here, so we'll try the simplest possible example just to illustrate. Simple join. by default, well, I have disabled one of the possible join orders with a hint. So the only possible option could be to start with the customer and then join with nation. And you can see the default plan is what you would expect. The index can be used, nested loop join, everything good. And we see that it's 3 seconds. Well, repeat to eliminate any caching effects. Almost 3 seconds. Good, quite fast, but disable the index usage. You can see hash and join is going to be used. Both tables are at naturally. .7, almost twice as faster. Again, the same. Of course, I don't pretend to say that the hash and join is better than the nested loop join. It's not true. But if you join some bigger result set with a small table, some kind of directory and so on, it's going to improve the performance. If you have a complex join of many tables with many limiting conditions, again, it makes a lot of sense to split it in 2 parts. Each of them will be optimized with a nested loop join using indexes, but then these 2 parts will be joined with a hash join. It's going to work really better than now. So it's not, again, not a silver bullet, but a solution that could improve some situations. And another solution we hope to address is to introduce hash and aggregation when the sorting will not be required to perform an aggregation. You can find a brief description of the algorithm here. Again, it's not an absolute solution, not an ultimate solution, because it works really good with non-selective grouping key. It means that there are very few groups with a lot of duplicates. A very few groups here for this algorithm means very short hash table, which is easy and fast lookup. If it would be very selective grouping key, we will end with millions items in the hash table, and lookups are going to be much slower. And actually, the sorting aggregation that is working now will be executed much faster. So again, it's only for some cases, but the practice shows that it's important. And one other area we are working on is to introduce some optimizer hints. Actually, it's not about those hints you were thinking about probably, that you use to point the dump optimizer to a clever decision. Nope, it's a completely different thing. There is one thing that whatever clever the optimizer it is, it cannot predict at all. This is whether you want to retrieve the whole result set as fast as possible, or just first few records. For example, show first 12 or 20 records in the grid, and then your users will be scratching their heads looking at those screens, and only then will press a page down to retrieve other data. But they want to see those first records, the first page of the grid, as fast as possible. The optimizer cannot predict that at all. This is your logic in your application. So this is the thing where we really need to suggest the optimizer what we are wanting really. So one kind of hints could be introduced in Firebird exactly for this purpose. And you can see what decisions could affect clause optimize for first rows. I see that my time is almost over. Just yet another slide. Most of this information has been already presented in the past year's conference, so you could find additional details in my presentation from the past year, but just a short list of the changes in the optimizer itself to use all the features I was presenting beforehand. So just take a look. As I have no other slides and no time to continue, I believe now you may ask your questions. You're free to find me in the hall or today or tomorrow and ask in any time. So just make your choice now or later. I will be here for both 2 days. And as far as I know, there will be a kind of round table this evening when you could ask whatever questions you have to the Firebird project team. So this is yet another chance to you to ask. But if you want something to ask right now, feel free. I have finished. Yeah.
Is there any plan to do backward index rate and index only, right?
We were thinking about that. Actually, this is not planned specifically for Firebird 3.0, but we are considering that. There are some problems with backward index navigation. They are addressable, but they require a lot of researchers. So we are not ready for that now. As for the index-only scans, there are some interesting ideas. Some of them could remind you the solutions used by the PostgreSQL team. And it does not require much changes in the ODS. And some other solutions is a complete index-only scans based on the different index structure, including the version information into the index and so on. But again, before even suggesting it to the public, we need a lot of tests, simulations, and so on. So we are working on that, but it's not for the prime time yet. Just for the future. It doesn't mean actually Firebird 4 or 5. As soon as we'll be ready for that. Okay, let's everybody go for the break, and then another speaker will continue. Thank you.